Hey, good afternoon everyone and welcome to the afternoon session. Today we have Zac Hatfield-Dodds talking. He's been writing Python for around 5 years with a focus on open source tools for fun and TB scale data analysis on Australia's national supercomputer. But
it's a big one.
Today he'll be talking about escape from auto manual testing with Hypothesis.
All right. Thank you. I guess the first question many of you have, well, what on earth is auto manual testing? Or possibly, what is Hypothesis? The good news is this talk will explain both. And if you're still confused, you can find my slides at this link after the talk. So I'm going to start by talking about a couple of different kinds of tests that you might have encountered, or maybe that you haven't heard of. So the first one is, what do I mean when I say an auto manual test? So a completely manual test is where a human does something. So you have a web app, you try to navigate to your homepage on your website and confirm that it's there. That's a manual test. An automated test is where you've written a program that tests your program for you. Because this is kind of what we do as programmers. We write programs to do our jobs for us and then hopefully get a more interesting job. So an auto manual test is a program to test a program that was handwritten by a human. This can include unit tests, integration tests, parameterized tests. There's a lot of kinds of tests. But fundamentally, if you write it and then a computer runs it, I call it an auto manual test. A generative test is where the computer writes part of the test for you. And with Hypothesis, this can be providing arguments to a test function in the same way that a parameterized decorator might do, or I won't be talking about this in detail today, Hypothesis can generate entire test programs where you can describe how to use your API, and Hypothesis will try to generate programs that raise some exception. The basic idea is that if you spend a lot of time writing tests, you might as well write a program that automates writing tests and then profit. For those who know the original comic, it goes on about ongoing development time, but the point of a library is that somebody else does that for you. And there are a bunch of interesting tests that I'm not going to talk about, like Sir not appearing in this film. There are diff tests where you compare the output of your program to known good output. And that's fundamentally what Python doc tests do. There are mutation tests which edit your code to check that your original test suite can find the new bug. There are coverage tests which let you find code that your test didn't actually execute, on the basis that code which wasn't executed by your tests can't possibly have been tested by your tests. A lot of people measure coverage in a percentage, but I actually think that's quite unhelpful. Because what you're really interested in is what part of my code is untested, not how much has been executed by my tests. And then there's a lot of static analysis tools like MyPy or PyLint, which will try to determine something about your code without running it at all. So property-based testing is a kind of generative test. The idea being that you have a general property of your code which should hold for any range of inputs. There's some kind of valid input, and if you can describe that, you can have a property-based test. So we're going to start with a simple example. Let's imagine, for the sake of the example, that you want to test that the sum of a list of integers is greater than the maximum. I know this is a stupid test. The idea is how you write it, not what you're testing. So our original version, we just have standard unit tests, right? Write the test, assert the thing we want to assert. We can not repeat ourselves by using the PyTest parameterized decorator. So we can pass it a sequence of inputs to try with, and PyTest will try each of those in turn and tell us which ones failed. Or with Hypothesis, you can simply say, given any list of any integers, this property should hold. And when we run this, Hypothesis tells us that we can't get the maximum of an empty list because there's no values in the list, so there's no maximum. So we go, okay, list of integers, but the minimum size of the list is 1, right? So lists of at least 1 integers. And then, of course, if there's 1 element in a list, the sum is the same as the maximum. But Hypothesis doesn't just give us any list with 1 number, it gives us the minimal list with 1 number, which is a list just containing 0. So okay, equal to or greater than. Let's try that. Anyone think of negative numbers? If you add up a list with a negative number, or more than one. The sum can be less than the maximum. But notice again, hypothesis has given us the smallest possible example of a list like this. So our final test goes for any list of integers where each integer is at least 0, and there's at least one of those integers in the list. The sum will be at least as large as the maximum. And this test passes. And hopefully, like me, at this point, you're pretty confident that that assertion is right, but you've also learned something about the code that you're testing, which you might not have found just by looking at it and writing test cases by hand. So I'm going to walk through a couple of the ways that you can describe inputs to your test with hypothesis. The first one, of course, if you want simple values, none, booleans, integers, floats, strings, times, dates, there are a lot of them, and hypothesis has functions which can generate them. Tiny link down the bottom, which you can see on the slides on GitHub, is a link to the documentation which describes this in detail. For types which have specific kinds of behavior, so for example, floating point numbers have a bunch of edge cases, as well as providing the minimum and maximum value so that you can constrain them to a particular range, you can also explicitly exclude or include infinity or not a number. Because let's be honest, nobody wants to deal with not a number. For collections, you give it the collection type, and then you also pass the elements of that collection. So we've already seen this, lists of integers, not just lists. Once you've got the basic thing down, you can change the things that you get from these strategies a little. So the map method of a strategy applies a function to whatever you draw. So if we take a strategy integers and we map string over it, the strategy will now generate strings of digits. Except it may also generate strings of digits which start with a minus sign if it drew a negative number. We can also map a multiplication by 2 if we only want to get even numbers, or filter a modulo 2 to exclude any numbers where the remainder is 0. This is an inefficient way to do it though. Filter is really designed for edge cases, and if you want odd numbers, you'd be better off multiplying by 2 and then adding 1. There are, of course, more advanced things if you need more complicated data structures. There are ways to call custom functions or classes with inputs that you describe, to generate recursive data such as JSON or other nested structures. You can draw new data parts inside your test function if the data that you need to run your test depends in some way on what's already happened. And finally, you can define your own custom strategies, which use any of the strategies provided by hypothesis mixed in with any Python code that you can write. The final way to get data for your test is to work out from looking at the code. Again, this is in the vein of we're programmers. Shouldn't the computer be doing this? Because if you have a schema is a way of describing what valid data is to a computer. And typically these are used for validating input, whether you're about to save it to a database, receive it from a user, in some way clean data that you don't trust. But in many cases, we can actually inspect the Python objects at runtime and go, for example, this is a regular expression. We know how those work, and we can generate for you strings that will always match that regular expression. Or if you use NumPy or pandas, you can get the data type and generate anything that could be an element in an array of that data type. Or if you have a function with type hints, hypothesis can inspect that and work out what type of argument to call it with, construct the strategy that will generate instances of that type, and then call it for you. There's a lot of detail. If you're interested, talk to me afterwards or check out the docs. But then there's the question, right, of, okay, we generate input. What tests do we write? Has anyone written property-based tests before? Can I see a show of hands? There's a few people. Awesome. My favorite one is called fuzzing. You don't assert anything, you just call your function. It is deeply embarrassing how helpful this is. You don't have to have any assertions in the test because it's just looking for assertions that happen inside the code that you're testing or exceptions of any kind. So remember in that first example where we discovered you can't take the maximum of an empty list? If that was production code, hopefully somewhere we would validate that the list was non-empty before we tried to call max on it. And this kind of combination of early validation and then checking later is why I love assertions so much. The best definition of assertion that I've found is that it's an expression which should always be true unless there's a bug in the program. So you don't use assertions to check that user input is correct. You don't use assertions to test that somebody called your function with the right argument. You use it where you think you might have made a mistake, where there's some complicated invariant or something where you're just not quite certain how the thing should work. You can put an assertion so that if something goes wrong, or that if your mental model of the code is not quite right, you find out as soon as it happens, not 30 calls later when the incorrect value eventually turns up somewhere. And so this idea of putting the assertions inside the code is often called design by contract. And there are a couple of libraries that can make that a lot easier. Most importantly, if you have these assertions embedded in your code, it means that the simple fuzzing pattern gives you integration tests completely for free. And so property-based testing, if you already do design by contract, is where you can restrict the inputs to your test even further. For example, the one with the sum and the maximum only works over a restricted set of lists of integers. And then you can make more specific assertions which further constrain the behavior of your program. Another great property to test is an invariant, anything that doesn't change or should always be true. So for example, if you take a list and you add the last element on again, taking the set should give you a different number of each element, but taking the set of a set should always give you an equal set. Or if you sort a list, you should always have the same elements as you started, maybe in a different order, but the elements should be the same. So if your code should have invariants, testing them with random data can often show up quite subtle bugs. There's another category of problems which are difficult to find a solution to, but easy to check whether or not a solution is correct. So if you have a code which is meant to find a solution, why not just check that it worked? Classic examples. Most cryptography rests on the idea that finding the prime factors of large numbers is very hard. But the reason we can use this for cryptography is that calculating the multiplication of numbers is actually very easy. Or if you're writing a programming language, tokenizing a string, breaking it up into the specific parts of a program, can be tricky. But checking that each token is a valid token and then sticking them back together, reasonably quick. There are a bunch of functions or bits of code which should round trip. So the way I actually started using Hypothesis was I had a library for a file format that I didn't trust enough. So I thought, well, what if I just generate random data, save it to disk, and read it back, right? If the library works, I should always have the same data at the end of that. And it turned out that I was right to be suspicious. It was dropping some white space in headers, and that was where my bugs were coming from. So dump to JSON, load to JSON, set an attribute, get an attribute, multiply, divide, except with 0. But the best pattern of all, if you're lucky enough to take advantage of it, is to compare your code to another bit of code which does the same thing that you trust. So if you're rewriting or refactoring something, you can feed both systems the same input and confirm that your new hotness is the same as the boring legacy thing. Or you can check that your fancy algorithm works the same way as the brute force thing. And maybe the brute force one is too slow to run in prod, particularly on large inputs or with adversarial examples, but I bet you can run it on tests, at least on a subset of your inputs. Or of course, if you're running multi-threaded, parallel, concurrent code. Has anyone ever had bugs from that? I'm impressed, not many of you. You can check that it works the same way with one thread as with 100. Last part of my talk is on some of the advanced tips specific to Hypothesis. Of course, it's a library for testing. It's designed for use by developers, and so you can configure a lot of different things. You can make it spit out verbosity, you can change the verbosity level, get debug information, or make it run in quiet mode. You can decide either globally or for each specific test how many test cases you want it to try. We default to 100, but maybe that's too slow for one of your tests, or maybe there's something where you just want to run 1,000,000 tests to be extra sure. You can decide where it caches examples that it fails. I'll get to that in a moment. Run it in deterministic mode, a whole bunch of stuff. Again, see the documentation. And you can configure this either in your setup code for your tests or as PyTest arguments. If you're using PyTest, you can pass arguments specific to Hypothesis. Whenever we talk about randomized inputs, people go, oh no, I hate flaky tests. We hate flaky tests too. So we have an invariant for Hypothesis that if a test fails, it is always possible to reproduce that failure. If you run hypothesis again on the same machine and you haven't messed with the database setting really badly, every failure will be stored in a database. So when you run the test again, it will pick up every example that it saw failing last time, run it again, and see if the bug is still there. So you never lose a bug, however hard it was to find in the first place. Or if it runs on CI and the database was on a worker which then got garbage collected and you can't get it, we also make sure that we try to do a couple of things. So for simple functions, we just print an example call to the function which should reproduce the bug. If it looks like there was randomness used, we also print the seed that would reproduce that. And if all else fails, we dump the entire state of the internals in a serialized format that lets you run the same test again deterministically. That one's less fun, but it always works. People also ask a lot about performance. Hypothesis is fast. There's a statistics option which you can check how fast it is or otherwise. And it'll give you things like the mean time of execution for each test case that you run, the percent of time spent generating data. And the reason I say hypothesis is fast is that's typically quite low. And you can even define custom events. So you can go essentially have a print statement somewhere in your function and have hypothesis tell you how often did it explore that part of your code. The other side of the performance story is running your code 100 times will usually be 100 times slower. Sometimes a little faster than that because of just-in-time compiling, but usually about 100 times slower. And because we also run the code under coverage so that we can profile what paths of execution we've already tested and try to prioritize the ones we haven't yet, there's a bit of an extra slowdown from that. It's still worth it. It makes us more effective at finding bugs, but you can disable the coverage checker if it's a pathological case. If you disable it, please tell us so that we can work out why that's going wrong and fix it for you. And the final part of my talk, here's a couple of people who are using hypothesis. Pandas, who's heard of pandas? Lots of people. Pandas uses hypothesis to check their date time handling. That when, for example, you take an array of date times or times and add an hour to it and subtract an hour to it, you get the same time back. That sounds really simple, right? One of my favorite ones that I've seen recently is an essay from a high school teacher who uses hypothesis to mark his students' assignments. So there's a link there, but the idea is it's a password checker. You have password rules, and it says at the top, don't worry, in big letters, this is a bad password rule. But you need at least 8 characters, at least a number, a letter, a symbol, and you can't have your username in the password. And all this one does is he defines text, so one part random text, mixed with a strategy that should always generate random passwords, so the test will try both. And then it simply runs the student code and the known good code and checks that they both give the same answer. And if it doesn't, it reports to the student the simplest example of an input that makes their code not work. OpenAPI is a way of specifying what REST APIs should do. And someone's written a really cool tool which will check that a REST API matches the specification by calling the REST API. So you can run this code, which is based on hypothesis, against a REST API which is implemented in any language because it speaks REST, not Python. Stripe uses hypothesis quite intensively and has even funded some features for us. They use it to test machine learning feature development for their fraud detection pipeline, and they don't give us details. And finally, it's 2018. What talk would be complete without blockchain? It turns out that Ethereum also does something with hypothesis. It looks like testing the Python virtual machine that they use to run an Ethereum virtual machine that they, I don't know, blockchain. Blockchain! And the last bit of this, of course, is the pitch. Hypothesis is an open source project. It's under the Mozilla public license, which is quite a permissive license. You can extend hypothesis under whatever license you like, but if you modify the core files, you have to share that with anyone you give them to. We actually try to mentor contributors. So if you come along to the sprints, it's not just like patches welcome, but I will actually help you write patches. And if you're a company that's using hypothesis or wants to use hypothesis, we offer both new feature development if you want to pay for that, or training sessions for anyone who's still confused after a talk. So that's pretty much the end of this pre-prepared section of the talk, and I would love to take questions from people.
Thank you, Zac, for a great talk. We're taking questions.
Thank you. I would like to know if you use hypothesis mixed with another auto-manual type of tests, and what type of tests, how would you split between, oh, test this bit with hypothesis, this bit of code, or this type of features, and test this bit with auto-manual, traditionally written tests? Thank you.
I mean, the universal answer is it depends. But what does it depend on? For specific edge cases, so if you're trying to test that a particular kind of input will raise a validation error, I would usually do that with a traditional manual unit test, simply because I don't think it's worth trying thousands of possible strings when the function should only accept integers. On the other hand, if it's something more complex or where there are many more possible kinds of input, I would usually tend to use hypothesis. You can also use hypothesis to supply some arguments and something like a PyTest parameterized to supply others. So if you want to try, for example, a specific couple of numbers plus other stuff, you can mix hypothesis with other libraries for that.
Thank you. Is hypothesis sort of self-hosting? Is hypothesis used to test hypothesis?
You bet it is. We test hypothesis with hypothesis on every supported version of Python, every supported version of Django, the last 5 versions of Pandas, 2 versions of NumPy, 2 versions of Faker, only 1 version of PyTZ because it's so stable. The test suite takes quite a long time because we test against everything, but it's a mixture of hypothesis tests and traditional unit tests.
Hi, it sounds like from your talk that you are a contributor to the hypothesis project. So yeah, I'm curious about what kind of stuff you've worked on within the project itself.
So for the last couple of months, I've been quite busy at work, and most of my contributions have been helping other contributors. So reviewing, fixing up documentation. I've cleared more CI issues than I care to think of. But features I've built, I did the work which lets it infer from type hints what arguments it should use. And there's a saying, right, that a pull request is like a puppy. When they're young, they're really cute. And then you take it home and you have to clean up after it. Turns out the typing runtime model has changed quite a bit over the last few versions of Python. And that's been an exciting journey keeping it working.
Hello. Hello. Your examples have been functions without side effects that just return something. Would you recommend hypothesis for testing some kind of interaction where the function doesn't return anything, but it's expected to have some kind of side effect?
Absolutely. The caveat on this is that your side effects have to be isolated within each test case that hypothesis tries in order for it to minimize the example correctly. Also, if it tries a number of tests and they have side effects between the test cases, it's very hard to reproduce that failure because hypothesis assumes that each test case is independent. But subject to that constraint, absolutely works for side effects. So for example, the Django integration will actually generate a model instance and save it to the database for you before running your test, and then handle clearing out the database between each test case.
Are there any more questions for Zac? Okay.
Hey Zac, thanks for the talk and thank you for the library. You mentioned Faker earlier in your list of things that you test with hypothesis, and that kind of crystallises something I'm trying to think about. So sometimes I use hypothesis when I've got like 3 or 4 well-defined inputs I can define properties for and go, great, there's a good application. But sometimes I've got this big blob of crazy data, like a person's name in Russian or whatever it might be. And then I go to a tool like Faker, I don't use that. It feels like I'm being lazy. I should be using hypothesis for that as well. Do you have a comment on when you would use one or the other?
So personally, I would always use hypothesis, and I may be a little biased, but I'll explain why. The way Faker works is it has essentially enormous lists and dictionaries of lists and tables of different kinds of inputs. So you can ask Faker for an email address, for example, and it will generate a random email address from the list of parts for you. Hypothesis, on the other hand, is both non-random in that sense. So with Faker tests, if they fail, they might pass again the next time and you never know why. But hypothesis is also much better at exploring edge cases that no one thought of. Because if nobody's added it to Faker's corpus of things to try, it can never try that. Whereas hypothesis, if it's describable, could generate that input. And Faker inputs are not minimized, where hypothesis does give you minimal counterexamples.
There's one question over there. Oh.
Wait for the microphone, please.
What other property-based testing frameworks influenced its development, and what are the significant differences between hypothesis and them?
So the most famous library for property-based testing is QuickCheck in Haskell, which was the first one, released around 1999. Hypothesis has taken inspiration from a number of other libraries in the way we design the API, and sometimes that's been things we imitated, and at other times it's been things we've avoided. The biggest architectural difference between hypothesis and any other fuzzing or shrinking tool that I know of is that a hypothesis input is generated from an underlying representation. Ask me about details later if you're really interested. But when it shrinks, it actually shrinks at the level of that underlying input, which means whatever constraints you had on the inputs to your test function will always be respected. So for example, if you've generated even numbers, every number that it tries to feed into your program will be even. Even will continue to be even while it is reducing that input to the minimal example for you. Other tools generally have test reduction at the level of values, so they try to make lists shorter or shrink numbers individually, but then they have to have an extra layer of filtering, which is relatively inefficient.
Any more questions? Okay, that looks like it. Thank you, Zac, once again for giving such a great talk. And here's a mug for our appreciation.